David Smith here with one more Flip Classroom math video. 3 tips before we start. First, you can increase or decrease the playback speed if that helps you get through the video. Second, you can pause the video at any time to catch up with your notes. Third, you can turn on the captions to watch my words go by on the bottom of your screen. Today's lesson covers inverse functions. Now this is an interesting idea. It's just one function is an inverse of the other if it undoes what the other one started. Now this is kind of like inverse operations. So you remember, like, multiplication and division are inverse operations. If you take any number, multiply it by 5, then divide it by 5, you're back where you started. So multiplication and division are inverse operations. So functions are way more complicated, but basically we can find inverse functions for functions and play with the algebra in there and the graphing. So let's take a look. Here's a definition. A function and its two functions are inverses if f of g of x is the same as g of f of x. And if you do the algebra on these two composite functions, they both should yield just an x. So we're going to give that a shot right now. What I want you to do is go ahead and pause the video and do f of g of x with these two functions. So go ahead and create the composite function and see what you get. Okay, so what I did is I just put my g of x function inside the f of x. So here's g of x. I put 1/3 x inside f of x, which is just 3x, and the 1/3 and the 3's cancel out and I get x. Now, we're not quite done showing that these are inverses. We need to do this case also. So pause the video and do g of f of x. Okay, g of f of x is just putting the f of x function inside the g of x function. So g of x is the 1/3, so that's on the outside. We're putting in the f of x in for x in the g function. So I have 1/3 times 3x, and again, that makes x. Okay. I want you to try that same algebraic process with these two functions and show that they are inverse functions. All right, let's see how you did. Now you're going to need to make sure your algebra skills are up to task because some of these functions, or the algebra required, gets a little bit more complicated. So first off, we're doing f of g of x. So I put g of x in here where x is in f of x. So I have 2 times parentheses x plus 1 over 2 minus 1. I do my distributive property, cancel my 2's, and I end up with x. So make sure you see how that works. Now we're going to try g of f of x, which means I put the f of x function in for x in the g of x. So g of x is x plus 1 over 2. So I just put my f of x right in for x in g of x, and then I just end up simplifying down and I get x. So indeed, these two are inverse functions. Okay, what I want you to do is do f of g of 2. And I want you to plug that in to the functions here. So first do g of 2, take that result, plug it into f of x right here where the x is, and see what you get. Okay, let's see how you did. So starting off with g over 2, I just plugged my 2 in for x here and I get 3 over 2. So g of 2 is 3/2. Then I take my 3/2 and I plug it into my f of x function. So that's 2 times 3/2 minus 1, which is 6/2 minus 1, which is 3 minus 1, which is 2. So that's my result. So what's interesting about that? Check this out. We did f of g of 2 and we got 2. That's what an inverse function does. It undoes what the first function did. So because these are inverse functions, if you put a number into one of them and then put that result into the next one, it's going to spit out the original number. Just like if you take a number and multiply it by 5, get that result, then divide it by 5, you wind up back at the number. Okay, just a quick board on notation. So we have a special notation to say what an inverse function is. So the inverse of f of x is written f to the minus 1 power. It's not really a power. What we say is f inverse of x. So that's how we note the inverse function. So hence, this is an IB word, right? So if the inverse of x is f inverse x, then we can write this statement that f of f inverse of x is the same as f inverse of f of x, and ultimately all of this is just x. So this is what we did on the last board using f and g of x. We're now just using f and f inverse of x. So make sure you understand this notation. You might see a test question that suddenly has an inverse on there. You need to know what that means so you know what to do. All right, here's a question. This is actually a little tricky. F of x is x squared, g of x is square root of x. Are they inverses? So pause the video for a minute and see if you can answer that question. Maybe do the algebra required to do that. All right, so here's what I did. I did g of f of x. So I just put the g of x, which is square root of x, in the squared one, and the square of the square root of x is indeed x. And the reverse is true. If I do g of f of x, I put the squared under the square root, but the same result, we get x. Now, this one brings out an interesting point. Are there any restrictions on the domains for each of these functions? Not there. We can put any number we want in for x in f of x. But g of x, we cannot put negative numbers in there. So strictly speaking, these are not inverses unless we specify that the domain is the set of all x such that x is greater than or equal to 0. Okay? Otherwise, we can't do that, because when we start pumping numbers into these functions, we're going to have a problem. And so here's how that shows up graphically. There is f of x equals x squared. We know this is a function because it passes the vertical line test. So vert line test, yes. Now there's another test. There's the horizontal line test. Boom, 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 like that. It doesn't pass that because the horizontal line crosses the function in two places. So horizontal line test, and that's a no. So x squared does not have an inverse unless you specify the domain. Okay, so that's the trick there. So you do have to pay attention to domains, especially when you have anything with a square root there. So another way we talk about this is that we say for functions to have inverses, they have to have 1 to 1 relationships. So for every x, there's one y, and for every y, there's one x. So you can see the parabola, the y equals x squared, doesn't have a 1 to 1, because for every y, there's possibly two x's. And that's what the horizontal line shows us. Whatever y value is here, we have two different x's that can come out. And so this is y equals x squared doesn't work. If you limit the domain, then this function looks like that. If it's just for x positive, for x greater than 1, and then that does work. So again, if we have the quadratic function in here, we just have to make sure we limit the domain. Let's do some work finding inverse functions for given functions. So this is algebra heavy. What you're going to do is, I got 4 steps for you. You're going to put the function into y equals form. I'll show you this in a minute, but I want to go over the steps first. Then you switch your x and y's. Then you solve for y. Then you put it back into inverse form. Okay, here's a problem. If f of x is 4x plus 2, find f inverse of x. So the first step is put it into y equals form. So I'm going to write y equals 4x plus 2. This is like equation form instead of function form. Now we switch the x and the y's. So step 2 would be x equals 4y plus 2. So I've just switched x and y. Now I solve for y. So I'm going to move my 2 over. X minus 2 equals 4y. Then I'm going to divide through by 4. And so that gives me y equals x minus 2 over 4. And then step 4, put it back in function form, only now I'm going to say f inverse of x equals x minus 2 over 4. Like that. Okay, I want you to try one. Pause the video and do all those steps, and let's see what you get for the inverse of h of x equals x minus 1 cubed minus 2. All right, let's see how you did. Take a moment, scan through the algebra, check your work, see if you have a question, see if you can figure it out. I'm going to move on. Now we're going to take a look at graphing and inverse functions, and we're going to find out that there's an interesting relationship between an inverse function and its graph. And that relationship we can exploit to make inverse graphs nice and quick. So check this out. I have my function, j of x, pretty straightforward linear function, 2x minus 1. This function, this line has a slope of 2 and a y-intercept of minus 1. Really straightforward. So first step here is to find j inverse of x, then graph both functions. So go ahead, pause the video, use the steps you just learned to find the inverse of j of x. All right, let's see how you did. I just did my trick. I switched my x and y, and I resolve for y. I get x plus 1 over 2. So that's j inverse of x is x plus 1 over 2. Now, I put this into slope-intercept form to make for nice and easy graphing. I'm not going to take the time to do this on my graphing calculator. If you want, by all means, put both of these graphs in your calculator and then come back and sketch them on the axes on your page. So this is 1/2 x plus 1/2. That's the slope-intercept or gradient-intercept form for that equation. So now, I want you to generate that graph. I'm going to go ahead and sketch a hand graph in just a sec, but I want you to pause the video and graph j inverse of x on the same graph as j of x. Okay. I'll call your attention to my graph here. You want to compare this to the graph that you just made and check it out. So first off, just check and see that your graph is good. Pause the video. If you're not sure what happened, take a moment, correct your work, make sure that you have good graphs. All right. Now, there's something going on in that graph that's interesting. I want you to pause the video and look at that and see if you can figure out what I'm talking about. There is a line here that kind of cuts these two exactly in the middle, and that line goes right through like this. This is the y equals x line. This line is a reflection line. It's like a mirror line. So every point on f of x, if you reflect straight across the y equals x line, we're going to go straight across. So that's a 90-degree angle. It's going to have a corresponding point on the f or the j inverse of x function. And you can see they both cross at the two functions cross together on the line. That makes sense because this line, this point is a reflection of itself. You can see that this line, this point is 0, -1, and this is -1, 0. So that's a reflection. So in fact, any point that's on the blue line, j of x, has a reflected point across y equals x on the j inverse of x line. So we can exploit that quite a bit. Okay, I would like you to sketch this function. F of x equals x squared, good old quadratic equation, the mother parabola, only it's not going to be a parabola this time because I'm specifying that you only want to use the set of all x such that x is greater than or equal to 0. So think for a minute about what that graph's going to look like, then I want you to go ahead and sketch that. Okay, if you got this, you did good. It's just the positive limb of the full y equals x squared parabola. We just don't have any of this because we've said we only want positive numbers for x, or the domain is positive, inclusive of 0, and then going all the way up to infinity. So if I specified the domain, I would say, here is my domain. Okay? So now I want you to sketch f inverse of x. I'm not saying find the function. We could do that pretty easily. I'm just going to say sketch it. So take a minute and use what we did in the last board with the y equals x line to sketch the inverse of this function. First step, I sketched my reflecting line, my y equals x line. I'm sorry, my green marker is a little bit light, but I think you should be able to see that. If you need to zoom in on that. So now that we have our reflecting line, I want you to carefully sketch the inverse of f of x on this set of axes. So check it out. I've just got another curving line that instead of curving up like that limb of a parabola, it curves across. Okay, that's it. That's all it does. And like we said before, every line that's on the f of x, this is f inverse of x, has a corresponding point. If you reflect it straight across, there's going to be a point there. So what is that point? Look at the graph, and we can tell that that point is the point 2, 4. Right? That's just 2 squared gives us 4. So that's the second point on my parabola. This is 1, 1. So then, if this point is a reflection of that point, what are the coordinates for that? We're just going to switch x and y. So this is the point 4, 2. Okay? This one is 1, 1. They both go through the same point here. So switching the x and y still gives us 1, 1. That point is 0, 0. So that's no change. Here's an interesting thought. This function should look familiar to you because you have graphed it already. Okay? So it's the inverse of f of x. We know how to find the inverse of f of x equals x squared. So pause the video and do that. Okay, here are the steps. To find f inverse of x, I first wrote it and switched it. I did the first 2 steps together. So I wrote it in equation form, and then I switched the y with the x. So now I have x equals y squared. Then I solve for y. So that just takes the square root of both sides. So y is the square root of x. So then f inverse of x is the square root of x. And this makes sense because if we square something, we can undo the squaring by taking the square root, and that undoes it. So that's an inverse operation. So this curving graph that starts at 0, you have seen. You have graphed these already in this chapter. That's a square root function. One last point. I'm going to call your attention to this over here. For inverse functions, the domain and the range are switched. And you can see that pretty clearly here. For this point, 2 is the domain, 4 is the range. We've switched it for the reflected point. So now we have 4 and 2. Okay, so 4 is the domain, 2 is the range. Okay, now this function's domain and range are the same. We're limited on the bottom end by 0 inclusive, and we're limited on the top end by positive infinity. So it's not going to show up if we write the domain and range because they are the same, but other functions won't be that way. So you can know that if you're doing your work right and you're listing your domain and range, for the inverse function, they should just be the opposite. Now that you've watched the video, take a moment to jot down any remaining questions so you can bring them to our next class. Remember, you can also come back to this video again and watch it for deeper understanding. If you liked or enjoyed the video, please click like or subscribe down below.